Okay, welcome to this video on Physics Unit 4, Physics on the Move, Edexcel Physics, and we're going to look at the particle physics part of Unit 4, and this is on Task 1. I'd just like to point out that it's definitely worth looking at the further mechanics and electric fields part of the course before you look at this part of the course. This sort of ties those two areas together, so I'd certainly look at those two before watching this. Okay, so the first part of this is building on a bit of work you done in GCSE on Rutherford scattering, and also building on some AS work on energies and diffraction, which is essentially the second part of the point over here. So if you're trying to make some synoptic links, try to make links back to the idea of how kinetic energy calculations and ideas about diffraction from AS can tie in with what we're doing here. And if you're looking for an AA star, think about how Rutherford scattering experiment can link with Coulomb's law, which we did in electromagnetic fields. So, explaining everything tasks are pretty straightforward. Explain how Rutherford determined the structure of an atom, include information about the size of the nucleus and the size of the atom. Okay, so remember the atom's larger than the nucleus. You've got to get your powers right. You're thinking about minus 15 and minus 12, the sort of sizes you're looking at there. And remember what he did was he fired alpha particles at a gold leaf. It was a scattering experiment to try to use the word scattered instead of deflected or reflected or anything along those sort of lines. And he did this experiment inside a vacuum. He fired alpha particles, which are essentially helium nucleus, and he fired them of fairly high kinetic energies at this gold leaf. Gold was used because it was easy to make into leaves and therefore easy to make into very thin thicknesses, and therefore it was very easy to get a very small number of atoms that the alpha particles would actually interact with and scatter off. It was done in a vacuum to prevent collisions with any other atoms that could have had an effect on the path of the alpha particles as they went through. Okay, so that's the main thing you should have been talking about that. You might want to tie in some of the observations and conclusions. I won't go through them all here, you know they come up very often, but remember the three main observations where most went straight through, some came back, some were deflected, some were scattered at large angles, or small angles, and some were and very few were scattered straight back, or back scattered, as the phrase is. And remember they tie in with observations, as conclusions, such as most of the atoms empty space. There was a charged central part of the atom, and that charge was positive and very dense. So explain why high velocities are required when we investigate the structure of matter. So high velocities, to get a high velocity, you need high energy. Okay, high velocities lead to high momentums, which lead to small de Broglie wavelengths. So what can actually happen there is the particle will actually behave as a wave and will therefore diffract through the spaces between atoms or the spaces between nuclei, and that allows us to investigate their structure. So that's what the fascination is with high velocities. We use high velocities so that we end up with high momentums and small wavelengths. Okay, so let's get stuck straight into these questions. Oh, there we go. So the first one, I'm going to sort of minimise the webcam. The webcam's not going to be used particularly much in this video, if I remember correctly. The first one talks through the experiment of alpha scattering, and they're asking us to draw the paths of the particles as they travel through and out of the atom. That's key, it says through and out, so you've got to draw it coming out. So path A is going to be pretty much a straight line, okay, and path B is going to be deflected and come out and away from the nucleus. So path A is pretty much a straight line, and B is going to have less deflection, so more deflection than A, so it's got a curved way as soon as it starts getting close to the nucleus. Remember, it follows the inverse square law of Coulomb's law. So he did the experiment in an evacuated chamber, just as we were talking about, and it's also mentioned over here. Why was it important that the alpha source was inside the container? Remember, the alpha would be absorbed by the container itself, so it can't be outside the container, it needs to be inside. Alpha radiation will be absorbed by any sort of plastic container, or even 5 centimeters there, so it's important the alpha was on the inside. The alpha particles have the same initial kinetic energy. Okay, because if they had differing kinetic energies, they would deflect or they would scatter by different amounts. So we only want to vary one main variable, and that's sort of like the distance the alpha particle is away from the nuclei. That's the main thing. So we want to make sure that speed is not having an effect on our observations. So the only two sort of things that we actually want to investigate, the two measurements we really want to be looking at, is how close we are to the nucleus and the angle of deflection that we get. That's why they have the same kinetic energy. So we're not varying the speed. And why was a container evacuated? We mentioned that before. So they don't collide with other atoms, as in atoms in any air. So therefore, no energy is lost. Okay. This is quite a common experiment. It's quite a common question. They're asking about the experiment, and they're asking you to outline the results and the conclusions. Okay, so the results, remember, were most passed through undeflected or unscattered, a few deflected at large angles. So that the main things from that were that, although if I remember correctly, the mark scheme for this question does say reflect. I genuinely don't like the word reflect on this, and we should really use the word deflect or scatter. And small nuclei, so the fact that most of them went straight through, there's a small nuclei that's mostly empty space, and it's a concentrated mass or concentrated charge in the middle. So we've got a relationship here. We're being asked how we could graphically plot to prove the relationship between n and theta. So they're saying that n is proportional to sine theta over 2, and all of that is to the power of x. So whenever you want to prove, whenever you want to determine the value of a power, you know you've got to log something. Okay. So the idea is if you logged both of these, if you had a graph, if you had a log-log graph essentially, if you had log of n against log of sine over 2, there we go. Okay, then the gradient of this should be equal to x. So whatever that graph looked like, the gradient of that would be x. So whenever you're trying to find a power, you need to do a log on both sides of this graph. Okay. So let me just show you that in terms of y equals mx plus c, and how we know it's a straight line through the origin, like so. So we have n. Let's say n is equal to sine. Well, there's not. It's just proportional to, so there's an idea of a constant. But let's do it like this. X. If we log both sides of this ends up being log n. If we log this side of it, that ends up bringing the x down in front of the log, and end up with sine theta over 2, like so. Okay, so you learn that in maths. Zoom in slightly. Okay. So you learn that in maths. Remember to look up logs on the internet if you're struggling with that, or come see me and I'll go through it with you. Natural logs we do a lot more of in Unit 5. Well, a bit when you do about capacitance as well, but definitely a lot more in Unit 5. Explain the meanings of the numbers in the symbol for gold nuclei. So remember they are the atomic numbers and the mass numbers. Okay, atomic number and mass numbers. So in other words, there's the number of protons at the bottom and neutrons and protons at the top. So this is sometimes called the proton number at the bottom, and this is called the nucleon number at the top. So essentially there's 197 nucleons, 79 of which are protons. So if you want neutrons, you take one away from the other, and you end up with 118. So there's 118 neutrons, 79 protons, and 197 neutrons plus protons. Okay, so that's GCSE. Show that the mass of an alpha particle is about 7 times 10 to the minus 27. Okay, so this is where we need to do 4 times essentially the mass of a proton, which is what we've got in the back. So 4 times the mass of a proton, and that gives you about 7 times 10 to the minus 27. So the mass of a proton from the back is 1.67 times 10 to the minus 27. If you don't know what I mean by the back, I mean the data sheet, which is usually in the back of a paper or towards the back of this ISP document. So 4 times 1.67 times 10 to the minus 27, so that 1.67 times 10 to the minus 27 is the mass of a proton, and that gives you about 7 times 10 to the 27. It's a nice easy one marker. Oops. In these experiments, an alpha particle may approach a gold nucleus to within a distance of 5 times 10 to the minus 14. Calculate electric force between separation. Okay, so electric force, Coulomb's law, straight away. I remember saying a few times this is related to Coulomb's law. You've got Q1, KQ1, Q2 over R squared. You know your K is a constant. You know your Q1 and your Q2. So what have we got? We've got an alpha particle and a gold nucleus. Okay, so I've got to think about this carefully. K is just a constant, so I'll leave that as K. The alpha particle has 2 protons, so that's 2 times 1.6 times 10 to the minus 19. That's the charge of a proton or charge of an electron, remember. But that's also going to be multiplied by 79 times the charge of an electron, 1.6 times 10 to the minus 19. The reason why, okay, is because that's your gold with 79 nuclei in it, 79 protons in it, sorry, to your helium with 2. And then you need to divide that by 5 times 10 to the minus 14. So remember to do 79 times 1.6 times 10 to the minus 19 and 2 times 1.6 times 10 to the minus 19. And you should have done it with something in the region of 15 newtons, which if you think about it is very large, especially when you consider the mass of the alpha particles actually moving. So if you applied F equals ma to this, it's going to have fairly large acceleration. Okay, right. So neutrons, like electrons, are often used to study crystal structure. A suitable de Broglie wavelength for a neutron will be 1 nanometer. So that's 1 times 10 to the minus 9. Explain why the neutrons must have a de Broglie wavelength in the order of this magnitude. Because remember, diffraction is what needs to take place. And remember that atomic spacing, or the distance between molecules, the distance between atoms, is about 1 nanometer. So the de Broglie wavelength and the distance between the molecules or the atoms must be similar for diffraction to take place. We know that from AS physics. We know that from GCSE physics as well, actually. And you know that atomic spacing is about a nanometer, and again from GCSE and the idea of nanotechnology. Given the mass of a neutron as 1.6 times 10 to the minus 27, which is very similar, or identical number to that of a proton right now, next year or later this year you learn that they're slightly different, ever so slightly. Calculate the kinetic energy of a neutron which has a de Broglie wavelength of 1.2 nanometers. Okay, right. So we'll go through this bit by bit. You have the de Broglie wavelength and you want the velocity. The reason why is they want kinetic energy. So when you figure out kinetic energy, you wanna get your v squared. So you can figure out the v from the first part of this and move it across into the other one. Okay. So you use the de Broglie wavelength is equal to Planck's constant divided by mass times velocity. In other words, momentum. So you know the mass, you know the de Broglie wavelength. So you rearrange for v. So v is therefore going to be equal to mass Planck's constant divided by mass times de Broglie wavelength. Then you take that velocity and put it into your half mv squared equation to figure out your kinetic energy. The mass, remember, is the same as the mass from before. Okay. Next question, question 4. This is a relatively long question part of the ISP. So scattering of an alpha particle by thin films of metal such as gold reveal details about the structure of the atom. For each of the 2 observations, give one clear deduction that can be made concerning the atomic structure. So remember, there were 3 main observations, so they're talking about 2 of them here. Most of them went straight through, so that means most of the atom is empty space. Some alpha particles deflected by angles greater than 90 degrees from their original direction. Okay, so if they're deflected by greater than 90 degrees, it means that within the atom is a central area of dense positive charge. That's the idea. Dense positive charge somewhere within the centre of this atom. Of the alpha particles that are deflected, most are deflected through angles much less than 90. So that makes sense. So most went straight through, but when you consider those that did get deflected, the majority of them are deflected by an angle less than 90. Explain why, from this observation alone, it is impossible to deduce the sign of the charge of the nucleus. You may use a diagram to deduce. You may use a diagram to illustrate your answer. Because remember, it could come from repulsion or attraction. Okay, it could have been repulsion from a positive nucleus or attraction to a negative nucleus. So that's your 2 marks for that. It pretty much is a 2-mark question, and that's your idea. So you could draw them out. So you could draw a positive nucleus and show that it's repelled, the positive alpha particle. You could draw a negative nucleus and show that it would have been attracted and still come out at an angle less than 90. It's the fact that it does angles greater than 90 that allowed us to figure out it was positive. The ratio of atomic diameter to nuclear diameter can be expressed in the form of 10 to the power of n, suggesting an approximate value of n. Okay, so remember, you've normally got somewhere in the region of 9 to 12-ish, generally 9 to 11 to 10. Sorry, times 10 to the minus 9 up to times 10 to the minus 11-ish for your atomic spacing, okay, or atomic diameter. The nuclear diameter is significantly smaller. That's times 10 to the minus 15. So the powers you're looking at are generally to the power of 6 difference or to the power of 4 difference. Anywhere between power of 4 to power of 6 difference between the two. So n would be any value 4, 5 or 6, and that would get you the marks. If you're at a minus because of the fact you've got it the other way around, that's fine as well. They accept that in the mark scheme. Okay, and that's everything for ISP task 1. Next task, we're going to start looking in a bit more detail at particle physics and getting stuck into the idea of cyclotrons, linear particle accelerators and synchrotrons, and also bubble chambers and how they work. Thank you for watching, guys.